Okay, thanks for the introduction. So as you said, my name is Ronak Buch. I'm a PhD candidate in the Parallel Programming Laboratory at the University of Illinois. And today we're going to have a tutorial on two separate topics. And both of these come from originally our work in the runtime system Charm++, but we've made both of them more applicable to parallel programming in the large, and in particular in MPI. So the two different topics I'm going to cover today are topology-aware mapping and load balancing. So let's get right into it. The first thing is topology-aware mapping. So the obvious question here is, what exactly is topology-aware mapping? Basically, the point of topology-aware mapping is we want to place tasks so that communicating tasks are closer in the machine topology. Really, the main goal here is to minimize off-node traffic, and in particular, link contention, because sometimes these can really slow down applications. It's not quite the same as a simple rank reordering. The big difference here is that we take into account the actual nodes that you get in an allocation and the shape of your allocation, if there are holes, things like that. So why is this important? As I said, execution time can sometimes be improved significantly by doing one of these mappings. We've seen things upwards of 2x in terms of performance increase for large jobs in some applications compared to the default mapping on Blue Waters. And this applies to even more of a degree on other machines as well. It's very dependent on the topology and application. So let's run through a quick example of what mapping actually looks like. So here we have a 2D application on a 2D torus. So this is somewhat simplified compared to what you would see realistically, but it's good for illustration. On the left here, you see the application domain. So we have a 2D application grid. Ranks are ordered by row, and every rank communicates to its neighbors. So we see here rank 5, for example, communicates to 1, 4, 6, and 9. Every cell you see in the grid here is an MPI task. So on the right side, you see the machine topology. This is before we've mapped the application at all. So let's say we map everything just directly into what the topology looks like. In this case, we have a really good mapping between the application and the machine topology, so it's very easy to do a good mapping. So since we have the same shape, we can just preserve the structure. And then we see very easily here that the node that contains rank 5 is one hop away from its neighbors, 1, 4, 6, and 9. So this is a very good mapping. We have a low distance to its neighbors, and we're not really oversubscribing links. However, say we have random mapping on the topology. In this case, you can see that now the distances between 5 and its neighbors are sometimes very high. For example, for node 6 and node 4, they're both using the same link for the first hop. So you're oversubscribing links now, and with a lot of traffic going on in the application, you can now hit bandwidth limits that slow your entire application down. So in general, bad placement will lead to longer paths. Longer paths leads to higher link utilization. Higher link utilization leads to link contention, and you get larger communication time. Particularly for communication-bound programs, this is a big problem. So in more quantitative data, say we have a 2D application with a 10 by 10 virtual grid, and we're mapping that to a 2D 10 by 10 torus. Again, we have near-neighbor communication. Each task just sends a message to its neighbor every iteration. And we use random shortest path for each pair of communicating ranks. So you can see here for a row ordering, our average and max hops and link load are just 1. So this is very good for us. But a random layout is much, much worse. We see much higher hop counts, much higher average load counts. To be more practical about it, say instead of having a native mapping to a 10 by 10 torus, we now map to a 5 by 20 torus. Now that simple algorithm that we use by row ordering doesn't look as good. We have much higher hop count, much higher link load, and it's a lot worse than the mapping that we found that's kind of close to what the optimal should be. So this is a more realistic scenario, and often it's hard to find these mappings that are good. So another thing you have to consider is how important mapping is for your application. It's not going to be a panacea for everything. Really, you have to look at the application communication patterns, the volume of communication, the ratio of computation to communication. Very importantly, the shape of your allocation. This can matter a lot, especially on a machine like Blue Waters. Job size, so the larger your job is, the further communication might have to go, so the more of an impact it can make. But in general, some applications, if it fit these criteria, can get more than 2x or 3x speed up in execution time. For example, we've seen this on Milk on Blue Waters. So how do we do this mapping? Really, the easiest thing to do is to use some sort of automated tool. And we can use this to change mappings and test to see if there are improvements. The worst case is you have no improvement, really. It can make things worse, but then you have the mapping to fall back on. One thing to remember is that it might only improve for certain job sizes and job shapes. So if you test it once and it doesn't help you, that doesn't necessarily mean this isn't good. Maybe on different allocations, it'll get a much stronger performance increase. The way that mapping works is you have to analyze the communication behavior of the application. So you need some knowledge of the application, as we went over a couple of slides ago. And sometimes it's hard to get this analytically by just looking at your source code, or even if you've developed the program from scratch, it can still be hard to get, for complex applications, the full priorities of how the communication happens. So to get these things, you often want to use profiling tools. So what profiling tools can you use? Here are a few that are useful for communication in particular. The first one is CRAPAT. So CRAPAT is included by default on Blue Waters. As you might guess from the name, it's from Cray. It's a large suite of performance analysis tools. One of the tools includes network level tracing. Another tool that's more general is this tool called MPIP. It's a link time library, so you don't need to recompile your application. And it presents statistical information on MPI calls, how many there were, how long they took, information like that. Finally, there's one that we have developed internally called Topo Profiler. Again, it's a link time library, collects information on MPI calls. Importantly, it includes topological information from the run. So, for example, things like the rank placement on a 3D torus on Blue Waters, a measure called hop bytes. I'll explain that in a couple slides. And it also extracts the communication graph, so the messages and bytes communicated between the MPI tasks or ranks in your application. And our tools use this to look at different mappings and do some analysis. So this is sort of the first step to getting an automatic profiling working. So then you combine the profiling tool output with mapping tools. So again, there are lots of ways you can do mapping. You could technically do this at runtime in your application. There are libraries to get the topological information, but doing that all yourself can be really difficult. So we don't recommend doing it unless you have a particular need to. There's a tool in CRAPAT called Grid Order that does something for mapping. It generally will place communicating tasks in the same node, but it doesn't place much importance to communicating nodes nearby. So depending on your communication pattern, this may or may not actually help that much. And it doesn't really deal with irregular patterns very well. There's another tool called TopoWare. Essentially what that does is assume near neighbor communication pattern in this grid that you provide, but you need to know the application grid shape, which isn't always easy to get. And it only works for some specific geometry. So we'll see later on in some results that this can be good for some things, but in other cases it won't work at all. And of course, we have a solution to these things. We have our own tool called GenM. This works with any MPI application, any system topology. The same way, it requires no source code changes. And it works with any communication pattern, including irregular ones. And basically what this does is just does a big search. So GenM in particular takes the comm graph that comes out of Topo Profiler as input. Then we try to minimize the average per rank hop bytes. So you see the formula for hop bytes there. It's basically just the number of bytes you send from one rank times its distance to its communicating neighbors. So bytes times distance, we sum all of that up, and we want to minimize that for every rank in the job. So this, of course, is an NP-hard problem, but we essentially do some sort of heuristic where we do multiple trials of random greedy search, and we usually get something that's pretty good. In particular, if you have a bunch of PEs in your job, we do a better job because we can now search more simultaneously. So to run GenM, it's very simple. You have to run your program once at a specific rank size using Topo Profiler, and you get this file called comgraph.txt or whatever else you want to call it. Then inside your batch script, you have an app run command that runs this program called mapper, that's part of GenM, that takes the comgraph as input. Mapper essentially goes through and does a bunch of searches and tries to find a good mapping based on the communication graph you pass in. Then you have to export this environment variable, mpitch rank reorder method equals 3. And what this does, you see at the bottom, it tells Apron to use a custom rank order from this file called mpitch rank order that gets generated by the mapper. Then you just run your regular program as you would, and it'll automatically use this file that we've generated in the job. So as a quick example, let's talk about Milk really fast. Milk is a lattice QCD application. It's a 4D lattice, 3 of which are spatial, 1 of which is time. It's really, really sensitive to placement because of its near-neighbor communication pattern. So it's a really good candidate for topology-aware mapping in particular. So looking at some profiling data, this is sort of a summary of some of the stuff Topo Profiler gives you. We see total execution time, hop bytes, idle time, point-to-point operation time. And you see that the average idle time and point-to-point are fairly significant. So converting to percentages, in terms of a total of execution time, the average idle time is 41% on this. So this is a default mapping on 8x8x8 shape with 16K tasks on blue waters. We see the average point-to-point time is 29%. We also have stuff for collectives that have sort of elided from the slide, but there's a lot more that Topo Profiler collects. But in any case, you can see that we have a lot of scope for topology aware mapping for this application. So looking at some results really fast. So on the x-axis, we have different shapes, 8 by 8 by 8, 11 by 6 by 8, and 11 by 2 by 24. And the y-axis, program execution time. So for the first 8 by 8 by 8 set, we have results for both TopoAware and GenM. And we see that both of them are fairly good compared to the default. But where topology aware mapping really shines is for these more irregular shapes. So you see the two right bars. Craze tool TopoAware doesn't get a good mapping for this. It doesn't work for these shapes. But you see for GenM, for the 11 by 2 by 24 case, for example, we get a very, very significant, almost 40% speed increase. So that was for 16K tasks. Here's for 8K ranks. Since this is a smaller job, we have usually less scope for communication-aware mapping. So you see that the performance results are a little bit less of a benefit, but in any case, it still helps a lot for particular shapes. Okay, so that's all the stuff on topology-aware mapping. There's more detail there. If you have questions, you can talk to me afterward or send us emails. But for now, I'm going to move on to load balancing. So just a little bit of background. In our studies, at least, we found that load balancing is critical to achieving good scalability and good performance on modern applications and modern systems. However, doing this in general is kind of hard. Modern machines are really complex. There's lots of hardware going on. There's lots of networks. And doing all this manually is extremely difficult. A lot of applications these days are multi-resolution, so you have a lot of variation in task granularity. You get some really big tasks, some really small tasks, and doing a naive distribution doesn't work that well. Often you also get multi-module sorts of tasks where you have different kinds of things going on in the same program. And in particular, lots of dynamic adaptive applications, AMR for example, can have very, very high variation across the execution, and they can be very, very data dependent. So in that context, what exactly is load imbalance? So we have a very sort of generic picture here. On the x-axis, processors, and the y-axis, useful work on that processor. So you see that there's a big disparity between some of the cores in this, and this is a very common case in modern applications. One of the big issues is that applications usually only complete when every processor is done. So whatever your maximum load is sort of your bound on computation time. With naive distributions, different processors get very different amounts of work, and you waste a lot of resources just waiting for other people to finish. So we want to get around this, and we have some guiding principles in designing load balancers and trying to fix this problem. So the biggest thing is what we call the golden rule of load balancing. So it's easy to take a look at this problem and say that what we really want to do is minimize the variance in load across processors. But it turns out that's not actually right. As an example, if you have 50,000 tasks on 500 processors, and every task is the same exact size, on your distribution, if every processor gets 99, except for the last 5 that get 199, or if every processor gets 101 except the last 5 which only get 1, the variance is identical, but the maximum is much, much higher in situation A. So really what we want to do is avoid having processors that are overloaded with work. We want to minimize the maximum load. And it's okay if some processors are idle. We just want to make sure no one takes too long. Okay, so another step is diagnosing load balance. So how do we do this? Often this is very clear because you see high idle time, you see this big distribution of work. But for a lot of applications, it's not always that obvious. Sometimes these things are hidden in synchronization overhead, for example. If you get to a collective operation MPI very early, then your profile might say that you're waiting in that collective operation while everyone else is doing other work that hasn't gone there yet. So it's not always idle time. Sometimes it shows up as synchronization overhead. Sometimes it shows up as collectives, as I just mentioned. Another thing you can do is just count the total amount of computation in every phase. Sometimes, if you saw Tom Quinn's talk from a couple days ago, he has an SPH and gravity phase in his application, and the load in each one is very different. So in Chang'e, we actually do load balancing between these phases to try to figure out different distributions to make those each go faster. So you have to make sure you count every phase and keep track of the balance when it changes from phase to phase. Finally, we actually get to balancing loads. Now, if you identified your application has load imbalance issues, we want to fix these things. So let's start from the basis here. Originally, this stuff all comes from Charm++, so I'll talk about how we do it in Charm. In Charm, all the objects basically are migratable, and this lets us get a lot of scope for moving stuff around. The other big aspect is that programs are usually over-decomposed. So we have a lot more objects than we have processors. This is good because it gives us high granularity on moving things around. If we have an object per processor, then if you move one object from an overloaded processor, that's probably going to be empty. So you need some fine-grained work to be able to do this well. In Charm, the runtime automatically measures PE and object load since it coordinates the execution. We have a bunch of different balancing algorithms that the user can select, and these every so often will calculate a new mapping. The runtime will move the objects around according to this mapping we get, and we continue execution. So I'm sure you've seen a lot of these plots already, but I just have a token one here. These are, for example, a scaling plot with load balancing in Charm++. So we can see here, without load balancing on 1K PEs, we get a little over 512 times speed up, but with load balancing, we get much closer to ideal scaling with 1024x speed up. And you see that continue all the way up to 32 kPEs, essentially, for this job. So for some applications, and we have a ton of literature on this, load balancing can be vital to getting good performance and good scaling performance in particular. So that's Charm++, but what about MPI? If you have an MPI application, you probably don't want to rewrite it. Usually a lot of work. So we have some solutions for that as well. Some of the big issues are that MPI ranks usually aren't migratable. Programs usually aren't that over-decomposed, and most of the MPI applications I've worked with, usually the number of ranks is less than or equal to the number of cores in your allocation. And there's also no automatic load measurement, so you have to figure out load balance issues dynamically and be able to use that to make decisions. However, if application developers can handle these things for us, we can provide the algorithms to actually do the mappings. And you have to take care of the measurement and the migration, everything like that. But we still have a lot of help to offer in terms of scheduling and moving stuff around. So one way you can do this is by this load balancing library. So essentially what we've done is we've taken a lot of the load balancing strategies we have in Charm++, and we have a lot of different ones. We have things that are compute-oriented, we have things that are communication-oriented, we have things like graph partitioners. There's a whole slew of different strategies that we have. And we've taken those and put those into a library. The whole point of this library is you can link it into an MPI program, and then you can use that to make object placement decisions. So the application just calls right in after collecting object load and object location data, and the library will return a new mapping given by whatever strategy you select. As I said before, we don't have a mechanism for migration because, in general, without knowledge of the application, we can't do that. So that's kind of up to the application developer if you choose to use this. So just a very brief overview. To use the load balancing library, we have one vital call. It's called charm lb assign obj. Basically, it takes the interface object that contains all the processor and load data. The new mapping is then returned in that object as well, and you select a strategy. So it's a fairly simple API to use. There's obviously some more calls than just this, but it's not too terribly complex. So that would help if you have the ability to add migration into your MPI program, but sometimes manually migrating isn't really that easy. So for example, if your application can't be decomposed into migratable data segments, it can be really hard to apply this library. However, we have more solutions for you. So we have a thing called adaptive MPI, we like to call AMPI. AMPI is an MPI implementation that we've made on top of Charm++, and it supports load balancing by just migrating entire ranks around. Often this doesn't require any code modifications to your MPI program. For most practical ones, it usually does. The biggest thing is it doesn't support global variables. We have some strategies to mitigate these things and to let people use MPI programs without too much difficulty on AMPI. So just to show results really fast, this is for Lulesh. You can see the purple line is just native MPI. We have two aspects of AMPI on display here. So another aspect of AMPI that can be very helpful is the over-decomposition thing. So here on the purple line, we have regular MPI. The blue line, we have AMPI with one virtual processor per physical processor. The green line, we changed the virtual processors to 8 for physical processor. And this essentially just lets us tile the application. So the benefits you see here are because of caching benefits. And then finally, when we take that and we add load balancing on top of that, we get an even better speed up. And this is for an application that doesn't have that much of a load imbalance problem. So for lots of other MPI applications, it can be even more effective than this. Yeah?
So it's hard to see on the graph. What's the actual improvement between the bottom two lines, the green one and the red one?
For this case, it's very minimal. I think it's on the order of like 5%. But like I said, other applications have been shown to be a lot more effective than this. This is just the first plot I had on hand, essentially. Okay, so to move on, we've addressed some cases for MPI, but what about accelerators? They're becoming really important these days, and a lot of applications get most of the performance from GPUs and things like that. So we've had a lot of history doing load balancing across CPUs, but when you add GPUs in the mix, it's a little more complicated. Some tasks you can only run on GPUs. Some tasks you have multiple implementations of, so you have to figure out where you should run them. And the performance for the same task can vary a lot based on what hardware target you choose. So in support of these, we have a couple new load balancing schemes in Charm that kind of address these problems. So I'll talk about them very briefly. So the first one is called vector load balancing. This is for for programs that have CPU-only tasks and GPU-only tasks, so not work that's fungible. What we do here is the Charm runtime measures load data for each target. So we measure every CPU task, we measure every GPU task, and for every object, we create this two-dimensional load vector rather than just having a single load value that we had before. So you have a CPU load part and a GPU load part. Then we have some algorithms to distribute this work to try to minimize the maximum load across both dimensions as much as possible. Really, we could do this with any values. We don't have to use CPU load and GPU load. We're looking at things like memory load in terms of bandwidth or in terms of size, and even application-specific parameters if that's better for some applications. So this is kind of a topic of active research, but we have some results for CPU and GPU load in particular. So this is a very synthetic example. We have 8 objects here. The CPU load on each of them is identical. They have an arithmetically increasing amount of GPU load. So if we use one of Charm's native load balancers, we see that the CPU load is basically even across all of the PEs, 4 PEs for 8 objects here, but the GPU load varies a lot. When we use the vector load balancer, now we get this ideal case where everything is perfectly balanced across our entire machine. This is obviously a very synthetic example, but we've seen similar results on more fully fledged applications. Another aspect of Excel load balancing, or heterogeneous load balancing, is something we call Excel load balancing. So this addresses the other case, where programs have fungible work that can be targeted to different hardware devices. It's different from vector because we don't have the static division of labor anymore. We can't just get 2 numbers because now one number can become the other one. So what we have to do here is find the optimal split to divide what percentage of tasks we should run on a CPU versus what percentage of tasks we should run on a GPU. So we have a lot of strategies to do this. Users can either specify that say, for this task I want 60% of the work to go on the CPU, 40% to go on the GPU, and just do that statically at runtime. We also have things that are more dynamic, where the runtime can try different allocations, measure how long it takes, and then try to find the best split point. So a couple of results for that. Here's, on the x-axis, we have percent device, what we call. So on the left side, it's all on the CPU. On the right side, it's all on the GPU. And in between, it's a continuum of different percentages. The y-axis here is runtime. So we want to minimize this curve. So here we see for a stencil application in 3 dimensions, our ideal is about 0.3, 0.4. So this is 30-40% of the stuff on the GPU. For a molecular dynamics example, again, same axes, we have about 65% to 70% on the GPU. So for different application domains, we can have radically different percentages of optimal split. So it's hard to guess these things ahead of time. It depends on your vectorization, depends on the machine. So usually we try to push this off to the runtime. It makes these things for us. It helps us try to find the right things to do. So just to wrap up very briefly, we have a lot more depth to the load balancing stuff that I've left out in the interest of time. So you have things like multi-strategy load balancing, where you can, based on the phase of your application, choose different ways of moving work around. We have some custom load metrics. Rather than using just the CPU measurement, you can provide application-specific things or other sorts of characteristics that we want to balance across the machine. There are a lot more details and depth to heterogeneous load balancing that I've left out in the interest of time. We have things to do automatic load balancing frequency and strategy selection using machine learning and things in that vein. And we also have the ability to write your own load balancing strategy, and it's really not that hard to do. So if you have interest in any of these things, please talk to us. We're more than happy to help. We're always looking for more users. Okay, so that's all I have. Here's my email address, our group's email address, and our group's website. Please reach out if you have any questions, and I'll be happy to take questions right now. Thanks.
different phases,
Mhm.
and each phase requires synchronization.
Okay.
And then the load balancing is different in the various phases. Can that be automated, or I mean, I of course try to do my best to do the load balancing well.
Yeah, so I think that the questions regarding load balancing in different phases, and in general, yes. Essentially, if you just create a call to the library after every phase, we can do the measurement. So it depends on your application to some degree. You might have to do some of this measurement yourself and then pass it into the library. But we can do load balancing in individual phases. We also have support in Charm, not in the library right now, but in Charm, you can provide a call to the load balancing library after every phase. Then we can select, based on what the current load we expect to be, whether it's worth moving work around for the next phase or not. So we have some intelligence on not moving around too much, because if you do it too often, then you just get lots of overhead of migrating work. So you have to be a little bit intelligent about it, but in general, yes. If it becomes a big issue, you can start doing it more and more frequently, and we have particular algorithms that will try to minimize communication, where instead of moving every object around, we can move just a few most important objects around to get as much load balance benefit as we can without introducing lots of communication overhead. So in general, yes, but I'll have to talk more specifically about your particular application.
Yeah, question from audience? Okay, I'm interested. So if we use the A API, it's really nice concept. Is there, what kind of profile tool can we use with the A API? Do you have a profiler?
So for profiling, do you mean profiling to measure things like load balance? Or, okay, so we have our own tool in Charm called Projections. So this is written by us, and the tracing is done by us as well. So it works with Charm natively, but since AMPI is built on top of Charm, it also has structures to do AMPI measurement. You can also use a lot of MPI profilers directly. They might require a little bit of modification because we capture MPI calls, but you can place yourself in between them and still get these things using something like MPIP.
Recently, Cray started adding Char++ to CrayPath.
Right.
So do you think AMPI also works on it?
That's a good question. I haven't tried it. It should, but no guarantee since we haven't touched that code. You have to reach out to Cray and see if they have things. But we're definitely interested in testing that, so I'll take a look in the future.